Alright, here's the same one from the notes. Says a sub n is the number of sequences using u, c, and a, length n, with 0 or 2 u's, and any number of c or a. And we're supposed to find a sub n. So the way to do it is to find the exponential generating function. Which will have a factor for each of those letters. These are ordered sequences, lists, or multi-permutations. So that means we need to use the exponential generating function, where we divide by the factorial to take care of those duplicates when we switch them around. It says 0 or 2 u's. So that actually is going to look like 1 plus x squared over 2. Sometimes I just write the 2, but it is 2 factorial, which comes out to 2. And x to the 0 is equal to 1. So that takes care of those 2 powers. And that's it. It says only 0 or 2. No other possibilities. And any number of c or a, so if it's any number, then it's power 0, power 1, and so on. And same thing for a, so I won't write them all. Dot, dot, dot means keeps going forever. So both of those are the ones we've seen a bunch now for the exponential generating functions. They turn out to be e to the x. Alright, so we have 1 plus x squared over 2 times e to the x times e to the x. And that's the exponential generating function. Now to find a sub n, a closed formula for it, I'm going to want to simplify that exponential generating function so that I can start using Maclaurin series. So I'll use my space here and I'll multiply this in. So times the 1 is e to the 2x, and then times x squared over 2. Another e to the 2x. Now I can see how to write them as Maclaurin series. I'm using just the basic Maclaurin series, the same one that I already used before for e to the x. And I get, so this is where I would stop for the EGF. But now, to get the a sub n as a formula, the next thing I do is e to the 2x, so it's summation and 2x to the n over n factorial. And for the rest of it, oh well, that's a plus, sorry, plus 1/2 summation x squared 2x to the n over n factorial n equals 0. So putting the x squared inside of the summation like that is fine. It's multiplying the whole function, and so it can be distributed. You can multiply it into the summation. It doesn't have an n in it, so x squared times the inside is fine the way it is. And so this is where now my goal is to get everything to have 3 features. First, x to the n, because the power n is the only thing that is going to be very easy to read back off the a sub n. Second, x to the n should be divided by n factorial. That has to match up to match the definition of an exponential generating function. which has a sub n times x to the n over n factorial. And finally, I would like it if all the summations started at the same value. N equals 0 would be nice. If they don't, it's not a deal breaker, because then you can just write a piecewise function and collect the ones that are maybe special, that don't all start at the same value. We had to do that for a previous problem. And eventually, you won't have to do that forever, because eventually you'll have the rest of the summation going out to infinity, and you can, for n greater than something, you'll have the same formula. And that'll be the last entry in your piecewise function. So, first let me get x to the n over n factorial as much as I can. So this will be 2 to the n, x to the n over n factorial, n equals 0 to infinity. And that part is done. It's got x to the n over n factorial. This, however, I have to add the exponents. So I'm stuck working with 2 to the n x to the n plus 2 over n factorial. Alright, so now I have x to the n plus 2, and I want x to the n. So I'll need to shift the index in that second sum. That means I'll replace every single n with n minus 2. When I replace every single n with n minus 2, which, by the way, you may have done at some point in the past, you're allowed to change variables if you want, as in the index counting variable. You can make it a k. I end up working with them so much I just write myself a note about here's the point where n becomes n minus 2. But if you want to make it n becomes k minus 2 to help it make more sense, it's fine. It's a dummy variable. It's just the counting variable. So the other thing to do is always, if you're a little unsure of whether you've done the indexing correctly, the shifting of the index, just test out a few values of that counting variable. For instance, in this one right here, it goes n equals 0 is the first entry, and it becomes 2 to the 0, x squared, 0 factorial. So after I index it, it should start there, same as that. So let's see. I'm probably going to run out of space on the board, but this part here, indexed, re-indexed, would be n equals 2 to infinity. So that's one I should more on the paper. When you make n equals 0 to infinity, re-indexed, n goes to n minus 2. That would be like saying n minus 2 equals 0, but I can just move the 2 over and say n equals 2. Then the rest would be 2 to the n minus 2, x to the n over n minus 2 factorial. All right. And now it has x to the n. That works well. And unfortunately now the power, well, this is true before, the power doesn't match the factorial. I need n factorial underneath. To get there, I just need to multiply on top and on bottom of the fraction by the same thing, which is always fine. Multiplying by 1 never changes the answer. So I'll multiply on top and bottom of that fraction by the rest of the factorial. So n minus 2 factorial, like if n was 7, that would start out at 5. I need n factorial, which would be 7 times 6 times 5 factorial. So if I multiply by n and n minus 1 on top and on the bottom I'll have n factorial. So multiply by n times n minus 1 on top and n times n minus 1 on the bottom. And now on the bottom, I'll have n factorial, and on the top, I'll have x to the n, and the rest of it on top will be a function of n, which is what I need. Let's see. Of course, the final answer is on the paper, but just in case, I want to put it on the board too. I think I can erase this piece here and finish the problem. Okay, so after multiplying on top and bottom by n times n minus 1, I have the current parts, which are 2 to the n, x to the n over n factorial, and I have 1/2, I have 2 to the n minus 2, x to the n times n minus 1 over n factorial. This is n times n minus 1 times n minus 2 all the way down. So just to show what's happening here, all that underneath is n factorial. So what I have left is summation n equal to 0 to infinity. Oh yeah, and this I mentioned as well. Now that I have n times n minus 1 here, when I plug in, if I wanted to plug in a 2, that would be fine, but I can also plug in a 0 or a 1. 0 makes the top 0, 1 makes the top 0, and instead of plugging in 0 or 1 won't change the output, just be adding 0 on. So I can write the entire thing as a summation 0 to infinity. And then I am kind of skipping a step here to save space. I should definitely go double check by plugging in some numbers. I'll do that. So I have 2 to the n, and then 1/2 2 to the n minus 2 times n minus 1. Okay. So I'll probably have to just do this on continued line here. 2 to the n, and then plus 1/2 2 to the n minus 2, which you could combine and make 2 to the n minus 3 if you wanted. Then times n minus 1. All that is times x to the n over n factorial. Ran out of room. So, let me just put it out front there. There's an x to the n here over n factorial. And squeeze that summation in. It'll be a little sloppier since you have it on paper as well. Between the two, should be able to make it legible. And then that lets me see a sub n. Before I write down that, let me double check. So at this point, when I plugged in n equals 0, I got 2 to the 0. Same here, 2 to the 0. When I plug in n equals 0 here, I get 2 to the 0, n factorial, x to the n plus 2. Here, of course, when I plug in n equals 0, I get a 0 from n times it. Same when I plug in n equals 1, I get a 0. So really, I should be double checking this one. When I plug in n equals 2, I get 2 to the 0, 2 to the 2 minus 2. That's the same as this one. And x to the, well, it'll be x to the 2, or 0 plus 2 over 2 factorial. Oh, I'm looking at the wrong one. That was over here. And I think that's right. My double check needs a bit more thought. Plug in x equal to 2 there. And on this one, when I get to x equal to 2, I'll have, of course, then I'll have that canceling going on, because I'll have 2 times 2 minus 1 on top, whereas I'll have 2 factorial underneath. They'll cancel out perfectly. So far it's working. On paper we could spread out and do a few more terms to make sure that I didn't make a mistake in the re-indexing, but good enough for now. I can write down a sub n as just the material that's in the parentheses, because it's multiplying x to the n over n factorial. So that comes out to 2 to the n. I'll combine this plus 2 to the n minus 3 times n times n minus 1. And then we did check that by plugging in n value on the notes.